Hello everyone, I'm Paul and today we're solving problem 2014, longest subsequence repeated k times. This is hard and this one is all about observation, so here we'll go through my thought process and solution. We're given a string s and an integer k, and we need to return the longest subsequence repeated k times in s. And if we find more than one subsequence with the maximum length, we need to return the lexicographically largest one. So let's say we have this. Let's say we get this string and k is 2. In case you don't know what a subsequence is, if we remove any character from here, this is a valid subsequence. If we remove all of these characters, the remaining characters form a valid subsequence. If we don't remove any character, we also have a valid subsequence. So we can get a subsequence from this by removing some or none of the characters. Now we're trying to find a subsequence here that's repeated k times, meaning 2 times. And here we have two options. For example, if we take the subsequence let, we have let here and we have let here. Given that k is 2, we are looking for let. So we are looking for this subsequence in this string. So we know this is valid, and we can also take ete. So we are looking for ete. And we have a subsequence with this. It's here, ete. So this is also valid, and both of these subsequences have a length of 3, and given that they have the same length and they are both valid, we need to keep the lexicographically largest one. So in this case we keep this, and this is what we return. Now this is the image for each subsequence, and down here we have the constraints, and here is the key for this problem. We know that both n and k are smaller or equal to 2000, and we also know that n is smaller than k times 8. Let's see what this means. Here we know that k is 2, so the maximum range in this case is 2 times 8, meaning 16. And here k is 2, meaning we need to find 2 subsequences here. This means that each subsequence can have at most a length of 7. So this has a length of 7, this has a length of 7 as a maximum. Because remember, the maximum value should be smaller than 16, and k is 2. Now let's say k is 3. Here n should be smaller than 3 times 8, meaning 24. And we need to find 3 subsequences in this range. So each subsequence will have a length of at most 7. And now with this I think you get the idea. What this means is each subsequence will have a length of 7 or less. So in the worst case, 7. Now another thing to notice here is that we can filter some characters from the original string. For example, let's take s. Here we see the character s only one time, but k is 2. And this means that this will never be part of the result, because it only appears one time. So we can build a frequency map from this, and we can filter every character that has a count smaller than k. So for example, here we see s one time, so we can remove this, and we also see c one time only, so we remove this, and we see the o one time and the d one time. So we remove all of this, and here we have 2 else and 2 equals to k. We have 1, 2, 3, 4 is, and 4 is greater than k, so we are good here. We have 1, 2 this, and 2 equals to k. So we are keeping with e, l, t. So these are our candidates. We know that we will be able to build a subsequence that's repeated at least 2 times with some of these candidates. And we also know that the largest subsequence will have a length of 7 as a maximum. This means we can brute force this with a time complexity of 2 to the power of 7. This is roughly 128. So we can brute force this, and this is how we can get every possible subsequence. And then we can multiply each of these subsequences with k and check if we have this subsequence on the original string, or even better, in this filtered string. And in this case we will use backtracking. So let's see how this works. Let's say this is the string, k is 2. Let's say we did our frequency map, we got our candidates, which are E, L, and T, and now we have these 3. So first we are trying to check if this is a valid subsequence. And remember, we need to get this subsequence k times. And this subsequence times k is E in this case, because k is 2. So we repeat this 1 time. Meaning now we are looking if we have this subsequence here in the string. And we do have this subsequence. Here we have an E, and here we have another E. The way to check if we have the subsequence is the following. We iterate this from left to right with an I pointer starting from here, index 0, and we are looking for EE. This is our target. So this is not an E, so we continue. Now we have an E, and this is the first character of our target. Let's say here we have a J pointer, so now we update the J pointer, and now we are looking for another E, so we update I, and here we have a T, so we update I again. Here we have an S, which is different from E, so we update I again. Here we have an L, so we update I again. And here we have another E, so we can update J. We reach the end, and given that J equals the length of the target, we return true here. And what this means is that this is a valid subsequence. We can find this subsequence here. So from here we can have 3 more branches, and we can move down 1 level. In one branch we have EE, we have another branch for EL, and another branch for ET. So for example, here we are checking if we have the target E in the string. And here we have E. So this is okay, meaning we can move down 1 more level. So here we have E. Here we have EL, and here we have EET. So for example, if we take this, we are looking for 6 E's, and here we only have 1, 2, 3, 4. So we don't have this subsequence. Now we are checking this, meaning if we have EEL, and here we have EE, and we don't have an L, so we can't continue here. Next we have EET, so we are looking for EET 2 times. And here we have EET, so we don't have this. And our result is currently EE, because this is the largest subsequence we've seen so far. So this is EE for the moment. Now we are checking if we have EL here, and we have ELE, and we don't have the next L, so this is not valid. Now we are looking for ET, and we have ET, so this is valid. And given that this subsequence has the same length of our maximum subsequence so far, and this is lexicographically larger than this, we need to replace this with ET. So from here we will have 3 more branches, and one of these branches will be ete. So we are looking for ete times k in the string, meaning ete because k is 2. And here we have ete. So this is good, and the size of this subsequence is greater than the size of this one, so we replace this with ete. And eventually here we'll have 3 more branches, and at some point we'll have le. So now we are looking for le in the string, and here we have le, so this is good. So from here we move 1 more level, we have 3 more branches here, and one of these branches will be let. So we are looking for let in the string, and here we have let. So this is good, and this has the same length of our current result, but this is lexicographically larger than this, so we need to replace this with let. And this will go on and on. For example, here we'll have 3 branches, and every time we will replace our result with the largest string, and if we get a string with the same length of the result, we keep the lexicographically larger, and finally we return the result, which in this case is let. So the backtracking here happens when we are checking if we have some subsequence times k, and if we don't have this, then we backtrack, meaning we move back 1 level and we continue this entire process. Time complexity for this will be roughly big O of n to build the frequency map, plus 2 to the power of 7 to do the backtracking, the brute force, times n, which is the length of the string, times the length of the subsequence times k. We'll call this target, so this is t. And space complexity will be roughly big O of n. So now let's go with the code, and hopefully you will get the idea. First we need to get our candidates, and for this we need to build a frequency map. So map equals default dictionary, and this will take a default value of 0 for every key, so we use the word int. And now for every character in the string, map at the character plus equal 1. Now our candidates, this will be initially an empty array. And now for every key and value in map.items, if the value is greater or equal to k, candidates dot append the corresponding key. And now we will build a helper function. We will call this is subsequence, and this will take some target, and here we will check if the target is a subsequence of the string. So there are 2 ways to do this. You can do this with an iterator, which is very efficient in Python because this iterator is based in C programming language. So you can use this, it equals iter s. So now we have an iterator, and we can return all C in it for C in target. So this works, and this is very fast, but I want to show you how to do this manually. So we can start with a j pointer, which is initially 0, and now for every character in the string, if the character equals target at j, we add 1 to j, and if j equals the length of the target. Here we can return true. Else, if we reach the end of this loop, we return false. So this and this is the same, but this is way faster. So now we can brute force every candidate and store the best subsequence in the result. So the result will be initially an empty string, and we will call this res for result. And now we will create our backtracking function, so we'll call this bt, and this will take a variable, we'll call this current. Here we will store our state, our subsequence, and if the length of current is greater than the length of self.res, self.res equals current, else if the length of current equals the length of self.res and current is lexicographically larger than self.res, self.res equals current. And now for every candidate in candidates, the next candidate will be current plus c, and if this next candidate times k is a valid subsequence, we can backtrack with this. So if is subsequence next times k bt next, and now we can call this function. So bt will use an empty string, and finally we return self.res. So this is it for the code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. And remember that if you use an iterator here instead of this, in terms of LeetCode runtime, the iterator is way more efficient. And there's one thing I wanted to show you, and it's that after we get the candidates, we can filter the original string. So we can say s equals an array with x for x in s if map at x is greater or equal to k. So just to be clear, this is for optimization, and if we combine this with the iterator approach instead of this, now this should be more efficient. So what's happening here is that if we filter this original string, next every time we run this function, we will iterate through fewer elements, so the overall runtime will be much better. So let's submit this and see if it works. And as you can see, this also works and it's very efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.